And hello again, YouTube. Welcome to our OpenFoam discussion on the heat flux utilities. This video we want to talk mainly about averaging the heat flux values that we saw in the file previously. Now, just want to correct a mistake that I probably made in the last video. So in the last video, I did say that the heat flux coefficient and the wall heat flux signs were kind of running opposite each other. So I did realize that I forgot to change the reference temperature inside the system control dictionary file. So I should change this T reference. If this was supposed to be the fluid reference temperature, I was supposed to change it to 600 degrees Kelvin, in addition to changing the change dictionary to 600 degrees Kelvin as well. So I'm running a file now just to see whether the signs truly do run opposite each other. So let's take a look at this, and let's take a look at oil and see the heat transfer coefficient. Okay, so we have negative heat transfer. Okay, again a negative heat transfer coefficient. All right, and we take a look at wall heat flux. Wall heat flux is all negative as well. Negative wall heat flux meaning to say that it looks as if the signs were correct, meaning to say that positive wall heat flux means to say that the fluid receives heat from the wall. This time it's a negative. So so we are like gaining heat from the oil. So I say again, when this wall heat flux value is positive, it means that the heat is flowing from the sphere to the oil. Now it is negative, meaning to say that the heat is flowing from the oil to the sphere. Okay, so that's it. So the thing that should be indifferent is the heat transfer coefficient. Alright, so in both cases it was negative, which probably means that, hey, probably something with our signages are wrong, but okay, there's probably some error that we need to fix. Maybe the T reference wasn't talking about the fluid temperature, it was supposed to be the solid temperature. No matter, with the utility, it was always a little tricky to get it right, because the documentation was a little sketchy in the sense that, hey, we have a cell temperature and we're subtracting some other temperature. Yeah, so here it is again. We have a cell temperature and then we have a wall temperature for the local heat, the reference temperature. And we have a fixed reference temperature. It is with this T ref over here. According to this, it looks like the reference temperature is supposed to be representative of a surface, right? It's supposed to be a representative of a surface, and this is supposed to be representative of the fluid, which wasn't what I inferred from looking at the C file of heat transfer coefficient. So if we take a look at the heat transfer coefficient, and then we take a look at the methods, okay, there is some HTC model. Okay, wrong one. Alright, this is the correct one. I just reloaded it back from the last video. Yeah, it looks like this is the T cell, and then this is TBF patch I, and yeah, it looks as if yeah, this one should be right when it talks about local temperature being the difference between the local fluid cell temperature and then the internal field temperature. And this, yeah, this is TBF, T boundary field. Okay. TC is the internal, is the fluid temperature. This is the patch temperature, which is the, I think, yeah, it does look like the boundary field temperature. Okay, then maybe I'm probably reading it wrong. Okay, yeah, but anyway, yeah, this is the one with the fixed reference temperature, and it's Tref minus TBF patch I. So, of course, if we use the local reference temperature, maybe the heat flux value, it should be positive. So we can try taking a look at that first. I'll just do a very quick one. Okay. Yeah, so just dealing with some of the heat flux stuff first. Control dictionary. So instead of fixed reference temperature, I'll just do local. Perhaps it will just give me the right gradient, so that the local heat transfer coefficient is what it's supposed to be. It is what do you call that? A positive value. Oh yeah, it should always be positive, because this is heat transfer coefficient should always be signed indifferent, regardless of which the heat flux traveling to or from the fluid. Okay, because if the heat flux is going this way, and then the temperature difference is this way, that means here should be a lower temperature than here. The formula kind of takes care of it for us, because the temperature differential direction is captured in the formula already. So anyway, so let's try this. Doing the local version, all clean and all run serial, and okay. Hopefully I get a positive value, unless the default value of the heat transfer coefficient is supposed to be negative. Okay, so let's see the one of the files there, and we take a look at the oil temperature, oil heat transfer coefficient. Okay, looks like it is still always negative. So it looks very weird. So probably something is a little funny with the code. Okay. And if we were to change it back to we change it back to 300, we can see if the sign changes. Okay. All clean, all run, serial, and of course we want, so I'm resetting this thing. Okay, and I want to change the Tref, of course, to 300, but of course that doesn't matter now, because what eventually yeah, because I've put it under comments, so there's a double / there. So let me put this in HTC model fixed reference temperature. Okay, so what I'm doing is I'm just putting it in comments in case I want to change it back later, so I can just switch as and when I like. Okay, so let's take a look at one oil VI heat transfer coefficient, always still negative again. It's kind of weird. Okay, it's very weird. This is a temperature boundary field, yeah, being less than, what do you call that, temperature field, yeah, 300 degrees. So it looks like the heat transfer coefficient is negative by default. even if we use this local heat transfer model, HTC model, which means it's right. Yeah, which means that the heat flux is kind of flowing in the opposite direction. All right. So yeah, heat flux should be flowing in the opposite direction from temperature gradient. That's right. Yeah, I think that kind of makes it logical. All right, so the heat flux should flow in the opposite direction from temperature gradient. So normally we try and have a modulus here in perhaps the formulas, but H should always be negative in this case to be correct. Okay, so hopefully, yeah. So what probably we read from I was reading from the C file was correct, meaning to say that the reference temperature should be a temperature that it's characteristic of the fluid rather than that of the surface. So TBF is the boundary field. It should be the surface temperature. Okay, so you should kind of expect the heat transfer coefficient to be negative. And regardless of, you know, whether the heat is flowing from or to the sphere, from the oil to the sphere or to the oil from the sphere. Yeah, so that means doesn't matter whether the oil is hotter than the sphere or the oil is colder than the sphere. The heat transfer coefficient should always be negative. So right, hopefully that clears things up. Let's take a look at the oil and then we take a look at the heat transfer coefficient T. Yeah, so it's negative, and the wall heat flux, there will be some directionality. So this time the wall is hotter than the oil. So the heat flux from the heat flux convention is positive, going towards into the oil. So this is the heat received by the oil. So yeah, just take note of that. Okay, so conclusion is that we were using the file correctly previously. Yeah, and the reference temperature is supposed to be a fluid reference temperature. And yeah, oopsie, that should be here. And I'll delete the space here and go. Okay. So, right. So now the thing is, of course, we want to have a representative heat transfer coefficient generated from this field. Right? We want to have a heat transfer coefficient from this field, and obviously we can't just take all these numbers and then, you know, have a kind of average. That's what they call ensemble average, which means that they just take all these entries and divide by 360, which is the number of entries they have here. So that's not quite viable. We need an area average, and OpenFoam does have a utility for us to do area averages. So good thing we have that, and that's what the main topic of this video was supposed to be. I just took like 13 minutes talking about checking whether the heat flux coefficient was right. Whether you know, the Tref that we are specifying, was it a temperature or a representative temperature of the fluid or the solid. So it was supposed to be a representative temperature of the fluid, and the result is that the heat transfer coefficient should always be negative. So that's what all the running back and forth is for. Okay, anyway, yeah, let's begin. Let's begin with looking at the, yeah, this one we kind of can just skip, and yeah, heat transfer coefficient we can skip. Yeah, so the function object I want to talk about is this thing called surface field value. And this is how we want to write it in. Now obviously there are a few things we need to put in like region, type, operation, etc., etc. And what we want to do is to get an area average. All right, this is area average over here. We want an area average of heat transfer coefficient. Of course, having an area average of the temperature of the surface will be very helpful as well. So we might want to do that in addition. Okay, now there is this thing called area normal average over here. Area normal average, which means the normal area. We use the normal area to normalize it. Why is that important and how is that different? So let's say you have a vector, you have a u coming in here. Let's say you have a surface like that. You have some fluid velocity coming in, and then you want the u per unit area, right? So you have a u, or rather UA, to kind of have a mass flow rate, right? So that's one way of doing it, the multiplication. But then you would say, okay, if let's say you want a projected area, because u is a vector, you want the projected area of this, then you need to do somewhat of a area integration or area averaging using the normal area. So the normal area is this area I'm talking about that I think should be in line with the vector. So there'll be some cosine theta or something like that. So you have a u dot a. All right. So that is some measurement of the flux or what have you, rather than just a simple u times a. Okay. So yeah, this is the kind of thing we're talking about if you're dealing with vectors. But since we're not dealing with vectors, we are dealing with scalars in this case, heat flux and temperature. Well, heat flux can be kind of thought of as a vector with three components, the qx, qy, and qz. But that's not what we are really dealing with here. We're dealing with the scalar version of the heat flux. So so that's what we want to kind of deal with here, because we have a scalar field of heat flux. We have a scalar field of heat flux. So instead of having three components, there's only one component per cell. If we were to take a look at the u, we will have, see, three components. Three components one in the x, y, and z direction. So this is a vector field, while the heat flux is a scalar field. Since the heat flux is a scalar field, we don't need to deal with all these direction complications, and therefore we can take a look. We can kind of look at the area average. Yeah. So of course, if we want to talk about area averaging, area normal averaging, we'll talk about that when we deal with vectors. Okay. Okay, so now let's see where we are. We have done the change dictionary. We have changed it back to 300 Kelvin for the fluid temperature, and we also have we also look at the system control dictionary, and we changed it back to the fixed reference temperature, and we have a T reference as 300. Okay, so this is healthy. This is what we want. Next thing we want to do is the average. So I'll just call it area average, and I'll have an open and close bracket as usual. Okay, I'm going to write this in, and now I'm going to put in the entries that we need. So I'm going to have a type and the library entry. Okay, so let's put the type and library entry in, and I insert and I paste it here as such. Next entry we need to have is called the fields. So the field names are as follows. Okay, so the fields, I'll put a fields entry here. Again, open, close, and semicolon. Remember, with for C++, non-curly brackets, the normal brackets, you always have to end it with a semicolon. Something like this libraries here where you have a, what do you call it, normal brackets with a semicolon. We have a right fields. I will put a null there. I do not need it to write the field for me. Okay. Unless you want all the extra little data. So right fields, no. So what's the next entry? Region type. Now what region type are we supposed to put in? Okay, if you take a look at this is the OpenFoam.org. So the region type here, it's called patch. All right. So this is some of the documentation. There are some commonalities and some differences between the surface field value for OpenFoam.org and OpenFoam.com. But they're similar enough such that we can try and use this the guides used by OpenFoam.org. Here, so region type, we just put it as patch, and the name, it will be our patch name. So let's put that in. Okay, region type, patch, name, I want the oil to sphere. Okay, so I'll just leave it like that. And of course, yes, I forgot, I need to put in the fields entry. One is for temperature and the other one is for the heat transfer coefficient. So what's the name of our heat transfer coefficient? We can take a look at our files here. So just copy and paste all of this, right? And then we'll just have our fingers crossed that this code works. But the good thing about this, the good thing about OpenFoam is that it will always give you good bug reports to see what is actually wrong. Okay. And of course, as for every multi-region case, we will need to specify the region as well. Okay. Let's see whether there's any other bit of data we need to put in. So we're not going to, these are optional entries, and well, we need to put in the operation as well. Operation is, remember, we want the area average. So let's put operation. This is very critical. Okay, so I'll just name this area average 1. And that should be it. Hopefully this works. So fingers crossed. Let's do an all clean. And we do a all run serial n. Okay, so good. We have an error. Why do I say it's good? Because it will help us to, yeah. Why do I say it's good? Because this error message tells us what do you call that? What's actually wrong. So foam fatal error, it says there's an invalid first character found, which is this apostrophe or this thing here. So let's go and get rid of that then. So where was that found? Of course, it's with our heat transfer coefficient here. So if we were to get rid of this, hopefully we can make the code run well. So that's it. Okay, let's do again our test run. So all run 0. So that's with changing the thing. So now again we can take a look at our chtMultiRegionFoam log. Apparently it's not working because it's not generating the files that we want. And okay, So what did it say? Entry field is not found in dictionary, area average 1. So let's go and look at what we typed. VI system control dictionary. Okay. Alright, so we spelled fields with an S there. So you have to take that out. Okay. Oopsie, sorry. Wrong one. Okay, let's see whether this actually works. Well, I doubt it will. The guide told us to write whether it's in the openfoam.org or openfoam.com version. The fields were always spelled with an S. Okay. Okay. Maybe the right fields function should be a yes. Because I wanted to, let's just put it a yes first. If not, there's really no point. And let's do all run serial n. And I'll just have this window open so that we can do a hot sphere and oil. We can take a look at the control dictionary, so I can like do editing instead of opening and closing files. So vi log chtMultiRegionFoam. So again, we have a field entry missing over here. Inside the dictionary, area average 1. So found from function boolean, read entry, word tfoam operation, blah blah blah. So this is puzzling. Okay, so that's not to do with the right field. Okay, maybe we can get rid of this heat transfer coefficient first, because this is the wild card in our game, so to speak. And this may mess up our calculations, because you know this name is kind of a little bit weird. Okay, it might cause some errors because the name is not it has all these special characters which may confuse the program. I'm not very sure, but we'll just run it with a T first, with a temperature field only. So I'll clean, or run serial. Clear. Okay, again we have an error. Okay, so it looks like this entry specifically wasn't the problem. Okay, let's see what else could have been going wrong. Whether there was any other thing that was missing. Okay, I think I found the problem. Okay, the type was not supposed to be heat transfer coefficient. It's supposed to be surface field value. Okay, there you go. No wonder it was asking for field. Okay, so in the heat transfer coefficient, we take a look at the entry it's supposed to have is this thing field. Field is supposed to be spelled without the S, because it's only looking for one field, and that's the temperature field. So yeah, I think that was a problem. So let's run it again. Okay. So split mesh regions is being run, which is good. And we have another error. Let's take a look at what the error says. Okay, so now it's looking for this thing called surface format. So let's put in this entry surface format. But what are we supposed to put in the surface format anyway? Okay, so if you take a look at here, the sampling data, surface format has all these files. We can either put in STL file, null, or anything. So according to this documentation, we can use null. So we can put null to suppress output, or we can put the STL file over here. So we can just put STL, or yeah, STL file. Okay. So let's write this in, and let's see what happens. So again, this is on the OpenFoam documentation. Because sampling data, it's a sampling data thing, and we have a surface format being used here. And that could give us some clue as to what to put inside. So we can just put all clean and all run again. Okay, so looks good. Let's take a look at the log. Okay, good. The log doesn't seem to be giving us any problems here. Okay. Surface format being given is an STL file. All right. So what does this do? Actually, it's not really what we wanted to do. That doesn't need to be a surface format output. So yeah, let's take a look at the post-processing. Anyway, that's where the files are supposed to be. And yeah, we see an area average file output, and we see a 0 and surface being put out there. So let's take a look at the surface. Okay, so looks like it's being conducted at every time step, which we actually don't really need. Probably reason why we didn't have the control is we didn't put this execute and write control at the right time. So we can just copy and paste this here as so that the next run we can have less of this coming out. But let's take a look at this cd6, and we take a look at the STL file that comes out. So this is what we have. These are the surface, the STL files that are being written. Probably, yeah, these are the files that are being written of the surface that's in question. So we can take a look at the post-processing, and oopsie, go up. Okay, looks like we don't have STL files here. Surface. Alright, I need to do a bit of a reload. Function F5. Hot sphere and oil. Okay, post-processing. That is strange. Post-processing and surface. Okay, there's no STL file here. No matter, never mind. So we do have all these being put out, but it's not really relevant to what we want. In fact, we probably want to suppress the output. But let's take a look at the surface value. Surface field value. Okay, so looks like for this we have, for the first 5 seconds, there is practically no heat flux being put out. Okay. Because the heat transfer coefficient is only being calculated every write time. You see, heat transfer coefficient is being calculated only at every write time. That means every 0.5 seconds we calculate the heat transfer coefficient. So you can see it kind of actually stays the same. But you can see the temperature is changing steadily, it's decreasing steadily, which is fine, which is kind of what we want to see for hot sphere cooling in oil, cooling from 49 plus something, and this will give us the area average, the temperature and heat flux values. Okay, so what if you want to suppress the output? We can actually try the word null, null. See, surface format. Okay, the other, I think the correct one that we should use is the word none, because yeah, the openfoam.org file actually tells you to put none there. I think this surface format is actually for something different, used for this sampling function. So it's a different function altogether. This sampling data function is a different post-processing tool altogether. So probably the syntax of being for the surface format entry is different. So we'll just use none to suppress the output, and of course we will have a area average, yes, and we will do a write and execute control using the write time entry, meaning to say it will execute for every 0.5 seconds where we want to actually put out the data. So surface format, we're going to put none, and we'll write it in, and okay, let's do an all clean, and we're going to run it again. And do an all run serial n. So yeah, we have data that's being generated out, and let's take a look at the post-processing this time. When we do an area average, we see the 0 file, and we see the surface field value data. See, it's very neat now. We've truncated it from 0.5 to every 0.5 seconds you compute. And that is actually enough of what we want to do for heat flux value. You can see that the heat flux, there's an average value now being averaged by the area. Okay, and then we also have a surface average temperature that's being recorded here. Of course, integrated by area. So you can see that the surface temperature is about 495 Kelvin, 493 Kelvin here, which is perfect. It makes perfect sense for us to have that kind of surface temperature. And of course, the heat transfer coefficient is negative, as we were discussing before. So hopefully there's no more doubt about it. And yeah, that's what we have for this video. So yeah, in summary, we were talking about the sign convention of the heat transfer coefficient. We spent the first 13 minutes doing that. And of course, we do the area average surface field value function, which helps us to find the average value of, let's say, our temperature and of course our heat transfer coefficient. So that is all I have for you this video. Hope it was helpful, especially in you learning how to do a surface average of the function, so that we can have solid values to compare with, let's say, a Nusselt number that we want to compute. So since we have a heat transfer coefficient here, we can actually just compute the Nusselt number there and then. Okay, so yeah, that's all I have for you today. Thanks for watching. I'll see you guys next time. Bye bye.